In this paper, we propose a novel task called Human Assisting Dexterous Grasping, which aims to assist humans in achieving dexterous grasping of various objects. The key distinction compared to conventional dexterous grasping is that in human assisting dexterous grasping, the human controls the movement of the wrist while the agent only controls the hand joint. This means that the agent not only needs to consider the object's information, but also the movement of the human hand, making it agent-centric. However, this task presents two challenges that need to be addressed. First, how should the agent grasp the object while considering the current relative pose between the user and the object? Second, when and at what speed should the agent execute the grasping action based on the trajectory history? To tackle the problem, we propose a novel two-stage framework that decomposes the task into two key components: learning a primitive policy through score matching and training a residual policy to complement the primitive policy using reinforcement learning. In the first stage, the primitive policy is trained to learn how to grasp by estimating the score function of the log density of a success grasping example sets, as shown in Part A. In the second stage, we focus on determining the appropriate timing for grasping, as shown in Part B. We train a residual policy that outputs a scaling action, AST, to determine how fast the finger joints should move along with the primitive action. Besides, primitive policy is not aware of the environment dynamics due to the offline training. We further require the residual policy to output a residual action, ART, to correct the scaled primitive action. By introducing the two-stage learning framework, our method surpasses all other baselines in terms of performance on 4,900 plus objects and 200 human trajectory patterns. Our approach exhibits faster convergence, achieves the highest success rate, and generates more human-like grasp poses. Additionally, our policy also maintains object stability during the grasping process. In this slide, we present the qualitative results of the final grasp poses obtained by different methods across different objects. Qualitative results shows the strengths of our approach in achieving human-like grasping poses across different objects. Our method not only excels in scenarios where grasping is straightforward, but also proves effective in more challenging cases. In this slide, we show that our method can grasp the different category objects according to different human trajectories, demonstrate the user awareness of our method. We further conduct real-world experiment to validate our method. In these experiments, we built a system, as shown in Part A, where we utilized the Leap Motion Controller as a hand tracking device to capture the wrist and hand poses of a human. However, for our robotic system, we only utilized the wrist pose and translated it to control the movement of the robot arm, and the agent will output the action of each hand joint to grasp the object according to human wrist moving. As shown in Part B, the robot hand initially aligns with the human wrist pose and subsequently follows the movement of the human hand. The agent infers the appropriate actions for each hand joint to execute the grasping task. When the human wrist is detected to lift for a certain distance, the hand automatically lifts up, moves towards a target box, and opens the fingers to release the object. A successful grasp is determined if the object can be transported to the box without falling before the hand opens. On the next slide, we present additional results showcasing the performance of our method on 10 different objects. In this slide, we present a demonstration of the successful grasps achieved by our method using 10 different ICB objects. For each object, we selected 2 grasp poses, and for each grasp pose, we conducted 5 tests, resulting in a total of 100 grasps. Our method achieved an average success rate of 66% across these grasping experiments.